Hey everybody, Backpack Hack here, coming at you with another trail tip, and today's video is going to be talking about series and parallel circuits. Now you're probably wondering, why do I need to know about electrical circuits to be a better hiker or camper or backpacker? Well, the answer is you don't. But if you're a person who is interested in getting into a solar panel system to power some of the things or all of the things in your house, using solar panels, batteries, inverters, and chargers, maybe you want to take your house off grid or become less dependent on the grid or have a backup system like I do. Perhaps you have an RV that you want to put solar panels in and have a battery system with an inverter so you could drive your electrical devices without having to fire up a noisy generator. It helps to understand series and parallel circuits. Now, most people are familiar with a parallel circuit to where they simply hook all the positives together and all the negatives together. And there's nothing wrong with them until you start getting into larger systems. For somebody who lives out of a van or a small RV, one or two solar panels and a couple of batteries will probably suffice. But if you've got a large RV system or you want to attach a system to your house or your business, you're going to be looking at series and parallel or series/parallel circuits. So I'm going to bring the camera in overhead and hopefully you can see what I'm doing here a little bit better. So let's get started with here on the table. Okay, we're going to use these 18500 batteries, which are 3.7 volts, 1000 milliamp hour in capacity, and we're going to use those for our demonstration. I'm going to turn my meter on here and let it boot up. It's a kind of complicated, expensive meter, but hopefully it'll get the point across. And I'm going to go to turn the backlight on. Maybe you can see this a little bit better. I'm just going to go to simply 1 decimal point. And these are 3.7, but they will actually measure a little bit higher because they are freshly charged and there's no load on them. But we will use 3.7 volts as an example. Now, most people are familiar with parallel circuits, and that's where you take the positive and the negative and you tie them all together. And I'm going to use these little strips of metal to help illustrate this point. Is I'm going to take one battery and put between there, and you can see that I have 4.1 volts. I can add another battery and my voltage does not change. And in fact, I can keep adding batteries and my voltage does not change. And I can keep adding batteries as long as I have a conductor between the batteries, which looks like that's going to be about it. I still have 4.1 volts. What I am adding is the capacity of each one of these together. I've got 1000 milliamps in each one of these, so since there's 7 here, I effectively have a 3.7 volt, 7000 milliamp hour battery pack here. Now that is a parallel circuit. When you tie all the positives together and all the negatives together, you have a parallel circuit. A series circuit is if you were to, I'll pull these off to make it a little bit easier to understand. A series circuit, again, we're going to go back here and we're going to measure our 4.1. Now if we take this one, and we will measure it. We should be very, very close. That is 4.1. So I'm going to take a little magnet, get a hold of it over here. I'll put over here, and I'm going to do a video. I've already done a video on one of these, on these magnets, and so I'll put that up here in the corner, up in the top right corner for you to see. But if I put these together, I should end up with about an 8.2 or 8.3 volts. 8.3. It added the voltages. Now if I measure this one, 8.3 plus 4.1, grab another battery here, put those together, and when I do this, I have 12.4. If I add yet another battery, I should be 16.4, 16.5. So at this point, I basically have a 14.8 volt, 1000 milliamp hour battery, whereas this in parallel, this is series and this is parallel. Now you may think, well, wait a minute. If this is 4000 milliamp hour and this is 1000, I'll take the 4000 any day because, well, you know, we know that there's more power here. Well, when you think about it, all else being equal, each one of these batteries has the same capacity in theory. So let's just say, for the sake of argument, that they are all perfectly identical. This will run a load equal to this. And to show you how that works, I'm going to bring in a sheet of paper here. And I'm going to put a series and a parallel circuit in together. Get these to stay where I want them to stay. Well, let's put this around the other way. Let's get the positive to the red side. Okay. Now, at this point, this is a 3.7 volt, 4000 milliamp hour battery pack. Whereas this one down here will be 14.8 volt, 1000 milliamp hour. Now, if we put these both on a 100-watt load, which one will last longer? Now, a lot of people will say this because 4000 milliamp hours is more than 1000 milliamp hours. But remember, we're adding our voltage here where we're adding our milliamp hour capacity here. We still are 3.7 volts here, but we are 14.8 down here. The difference is going to be how much current is flowing in these wires. Now, the formula in Ohm's law is current equals power divided by electromotive force. This is amps, this is watts, and this is volts. So I'm going to get my calculator out and we're going to run some numbers here. We have, let me get this back up here where you can see it. Here, the amperage will equals 1000 watts divided by 3.7. 100 divided by 3.7 equals 27, let's just say 27 amps. So there's 27 amps running through both of these wires. This one is a 14.8 volt 1000 milliamp circuit. So again, the same formula will be the amperage equals 100 watts divided by 14.8. And we get let's just round it off to 6.8. 6.8 amps running through each one of these wires. The reason these are equal is because there is each one of these is supplying 6.8 amps of power, as are these. There is actually 6.8 amps drawing through here, but there is 13.5 here and 20.3 here. And the same thing here, 6.8. This one is 13.5. This one's carrying 20.3. And finally, you get over here to the 27 here and the 27 here. That's why these are equal in terms of longevity. The advantage to doing a series circuit is going to be your amp draw. Now, if you have a set of solar panels at a long distance away, you're going to see significant line loss at 27 amps because you have to have a bigger wire. Whereas here you've only got 7 amps, you can carry that load a lot farther because you only are drawing 6.8 amps. This comes into a significant play when you start to talk about solar panels that are away from your house. A lot of people, it's very, very common to put your solar panels on your roof, but sometimes that's not possible, so they have to be a long distance away, sometimes several hundred yards. And this is where it starts to come into play to where you want your series circuits so you can increase that voltage, drop your line loss for a long distance between the panel and your charger and to get the power to your batteries. Now, one other combination I want to show you is called a series/parallel circuit. I'm going to bring my meter back into view here and turn on the light. And I'm going to put my leads back on. Now, this is a series circuit. Yep, forgot I was going to leave my leads on here. I'm going to take those batteries out because I'm going to do a little bit more. Those are strong batteries. Oh man, those are really strong batteries. I got to tell you, I should do a series on those. I'm going to put these clips back on these metal bars, and we're going to build a series/parallel battery pack. Now again, this is a series battery. I should have my 4.2 volts here. I'm trying to keep all this in view of the camera, or my 8.3 volts. This would be an 8.3 volt, 1000 milliamp battery. I'm going to put another 2 in here, and again, I have 8.3 volts, but now I have 2000 milliamp hours. If I put a third battery in here, I now have, this came off. Didn't expect to do that. I now have an 8.3, 3000 milliamp hour. Get it all to line up so I could read the meter, but there you, let go again. There is your voltage, 8.3, but I have 3000 milliamp hours. This is important to understand, especially when you are starting to get into solar panels. And I'm going to get rid of all this out of the way and bring in another image here and bring up back my calculator because we're going to be doing some more math. Most common, let's just say these are each 100 watt. They're designed for 12 volt systems, but they can generally put out 18 to 20 volts. I have 4 panels on my house, and I routinely see 80 volts out of my 4 panels that are wired in series. So what is the difference between this and this? This is still going to, these are still the same panels. Now this is the individual panel, not the bank. These are individual panels. Let me show you the difference. Let me get to this first. I forgot to do this. Here is my Goal Zero panel, or my Goal Zero solar panel. And I'm going to try to do this, and I'm going to turn the lights off so you can get an idea of what I'm talking about here. I'm going to get some sort of voltage here. I'm getting about 2.2 volts. That's going to drop down. It's going to drop down to about 1.5, 1.4. That is the voltage. I'm going to try to hold on to that so it doesn't get this up there where you can see it a little bit better. See, I'm at 1.5 volts, 1.3. I'm going to use my flashlight to simulate the sun. Now, striking it across the side like this, you can see that I still don't have enough voltage to charge up a 12 volt battery. But as I raise it up, Then it finally gets to the point now that I'm at the point that I can see that I'm getting good voltage to where I could charge a battery. And as I get up higher and higher and higher, the voltage goes up until it peaks. And then as the sun goes down, the voltage is going to start to drop. And eventually it will drop down to the point where I can't use the charger, the solar panels, to charge my batteries anymore. This becomes very, very important when designing a solar system, because when you consider series and parallel circuits, I am going to have a 12 volt 4,000 watt. Now again, let's do the math. What is the current on this? Well, remember, it's the amperage equals the watts over the volts. So we bring in our calculator again. We want to calculate what size we need. We have 400 watts. Divide that by 12 volts, and this is 33.3 amps. That's a pretty good sized wire. However, this one, because I'm in series, I have a 48 volt 400 watt. So now I'm going to take 400 divided by 48, and I'm now down to 8.3 amps. I can use a smaller wire. This also allows me to do two things. I can put the panels farther from the controller. I can also, because I am charging, I'm going down to 12 volt batteries. Let's say early in the morning when the sun is very, very low, and not up here, but it's very, very low. Let's say I get 4 volts out of each one of these. They're all producing 4 volts. I still have a 4 volt output. So I don't have the voltage to even consider trying to start charging my batteries. But here the voltage adds. I now have 16 volts both early in the morning and late in the evening. So I can start charging earlier in the day, stay charging later in the afternoon. I can charge, or let's say it's just lightly overcast or medium overcast, where each one of these is putting out 4 volts. On a cloudy day, this is not going to charge. I'm going to turn the battery or the lights back on because I'm done with that meter or the solar panel. These are still putting out 4 volts. I have 4 volts coming to my charger. These are putting out 4 volts individually, but collectively they're putting out 16 volts. That is enough to induce enough charge or enough voltage to start charging my 12 volt batteries. This is where the economy of doing a series circuit can be beneficial. Now, if you want to increase your capacity, you could add 4 more panels in series and then parallel them with these 4 panels. And you could do that same way like I did with the pairs of batteries before. You could keep adding sets of 4. Or you could just go to 2. You could do this, these 2 in series, these 2 in series, and put them in parallel with these 2. So your circuit would be, and that's how that would work. You could do a series parallel circuit. So these 2 are in series, these 2 are in series, and then these 2 are in parallel to these 2. So that's how understanding how these things work can help you make a more economical system. And there you have it. That's the difference between series, parallel, and series/parallel circuits. Hopefully I've explained it well enough that you can at least understand it. If you want to design your own system, or you're going to have a system designed, maybe you can understand what they're talking about when they explain how they're doing things. and maybe you can interject some ideas of your own and maybe save a little bit of money. There is a financial gain to be made by making these decisions between one or the other or both. So with that, I'm going to wrap this video up. Be sure to like, subscribe, comment, and share my videos. I'd like to hear from you in the comments below. Wrap this video up. This is Backpack Hack coming at you with this trail tip. Be safe out there, and I'll see you out there on the trail.